Hi, my name is Kieran Buckingham.
And I'm Isaac, and this is our speed of sound measurement project.
Okay, so here's a brief tour of our setup. As you can see, it's not quite as flashy as our previous projects, considering that it's all inside a small cardboard box, but don't let the size of it fool you, because there's more to this little box than meets the eye. With it, our goal is to measure the time it takes for echoes produced by the ultrasonic sensor to return over a round-trip distance of 12 centimeters, while also measuring the local temperature. Although it has many connections, as you can see, the design is relatively simple, as we'll soon find out.
Here's the circuit in action. It collects the data with the press of a button, displaying it on the screen right here, while storing it in an SD card connected to our board.
Okay, so here's the code. At the top, we have initializing, the LCD pin setup, and the ultrasonic pin setup, as well as some constant and variable calculations. All this stuff is very self-explanatory. The function up top is going to be the one corresponding with our temperature sensor, and below that with the ultrasonic sensor. The ultrasonic sensor works by sending out a high-frequency pulse and detecting the time that it takes for that to reflect and come back. Beneath that, we have the corresponding calculations for distance and velocity. Lastly, we have the LCD display displaying velocity in meters per second and temperature in degrees Celsius. And beneath that, we have the optional serial monitor output, which we don't end up using while taking data.
A brief rundown of our physical setup, describing the actual Arduino apparatus that makes all this data collection possible. To the left of the screen is our apparatus, and to the right is a simplified description of what's actually going on. Keep in mind that the simplified description doesn't include the button or the temperature sensor, but I'll clarify that later as the video progresses. Here we have the 9-volt battery that supplied power to our board as it collected data outside and away from the computer. It's simply connected to the power pin section of the board. Additionally, we have the SD card module located in the orange circle right here, which allowed the data to be collected and stored as a text file for future use, such as the plotting we made later in the video. Here we have the LCD screen connected to the digital pin section of the Arduino board, which essentially unifies all the sensor data. The screen itself shows the timing data as well as the temperature data read from the ultrasonic and temperature sensors in real time without the need for Wi-Fi or any sort of computer connection, making it a very versatile measurement device. To make the text on the LCD screen readable, a potentiometer is wired to adjust the display contrast on the screen. One end is connected to 5 volts, the other to ground, and the middle pin goes to the VO pin on the LCD circuit.
So for this experiment, I decided to take temperatures Friday night in San Luis Obispo. I was able to take temperatures from about 3 p.m. to 6 p.m. until the battery died. And then I got some new batteries and I was able to take temperatures from 7 p.m. to 9 p.m. I also had to go back to my hometown on Saturday, so that's in Northern California, and it's a lot hotter up there right now. So on Saturday night, I was able to take temperatures from probably 100 degrees to about 70 degrees, which was the max that we got in slow. So we actually got a bigger data set than you'll probably see on some other projects, and I think that helped out our data accuracy a lot. All right, so here's a look at our raw data from the Arduino. We got values ranging from 15 degrees Celsius to 35 degrees Celsius. And if you look at this graph, there's definitely some outliers above, 380 meters per second and below 330 meters per second. So on the next graph, we're going to go ahead and take off those outliers and see if that cleans up our data a little bit. I would say visually, the graph looks okay. It's not off by too much. According to the naked eye, it looks like less than 10 meters per second. But that R squared value and the return on the equation does not quite fit what we're hoping for, and we know we can do better. So let's go ahead and take off those outliers and see what it looks like. Okay, here's an updated graph with those outliers removed. So now we only have values that are within plus or minus 10 meters per second of the speed of sound. And this greatly increased our R squared value. If you can see it jumped by almost a factor of 10. Our slope as well increased closer to that 0.6 that we get from the theoretical equation. And the y-intercept is also approaching the 331 from the theoretical equation. But there's no reason to think that we can't do a little better and try and get that slope up a little bit and that y-intercept down even further. So let's go ahead and average the echo times over each distinct measured temperature. Okay, in doing that, we see the r squared value has increased to over 1/2. We also see the slope has increased, while the y-intercept has basically not changed. And I feel obligated to say that our measured distance from the ultrasonic sensor to the wall was 6 centimeters, but there definitely could be some error in that. So in all these graphs, the calculated velocity is based off of a distance of 11.75 centimeters. I believe this to be an acceptable adjustment based off the way we measured the distance in class using a flexible ruler. But lowering that distance any further to increase the accuracy of the data, I feel that's just, that would just be dishonest. The goal of this project was to explore how temperature affects the speed of sound in air, and also to explore the reliability of the Arduino sensors and their data against the known physical model. In doing this, we went much more in depth on the data analysis and correction than on previous problems, and this is due to environmental factors such as temperature fluctuations, ambient noise, and sensor delays.
To add on to what Kieran said, we learned of the importance of designing our experimental apparatus with greater awareness of both environmental and electrical variables that could interfere with our results. This meant not only accounting for obvious external factors like ambient temperature or reflections affecting sensor readings, but also critically evaluating potential issues hidden in our own Arduino code structure or wiring, such as with signal noise, timing errors, or just improper grounding of circuitry. Through this process, however, we became more intentional in identifying and minimizing confounding variables. And fortunately, beyond these concerns, there were no significant issues affecting our observations, as any data points that did appear anomalous were clearly inconsistent with established physical principles, making them easy to identify and omit from our final analysis. And from the analysis from early on, we clearly see that our data is quite consistent with theoretical predictions for the speed of sound, which is around 343 meters per second. But anyways, guys, thank you so much for watching. That concludes our Project 3 video presentation, or whatever, on measuring the speed of sound with an Arduino apparatus. Thank you so much for watching once again, and a huge shout out to Dr. Fernzer for being an absolute legend this quarter. But anyways, yeah, that's it.